we're almost done with all the basic stuff, and today we're going to talk about the Maxwell energy stress tensor. Now, I am very, very sure that you have not seen this before. So we're going to slow down a little bit. So on that, off this recording, we discussed about the pace of the class, and it's the first time I'm teaching the class. So I want to make sure that I'm not losing you all. So there's a reason we've been going pretty fast. First of all, there's this is material that you're supposed to have seen before, but you may have not seen it at this level. And one of the things that I personally struggled with when I started university, period, was that I remember this vividly, that my first calculus class. So my high school system is different in Holland. It's a track system. So I had multivariable calculus in high school. So and then I go to university, and everybody there mandatory has had to take their high school calculus class, and so everybody knows this. So sure enough, week one in the proper calculus course, they blaze through the entire material of 3 years of calculus that you did in high school, and I was quite shocked. And the thing is that we didn't slow down. It kept going at that pace. So the thing that I had to get used to was that if I wanted to see things in action, if I wanted to see, okay, so can I revisit this point? Okay, what does it look like if I tweak the situation a little bit like this, a little bit like that? I had to do it myself, because otherwise I was not going to be able to ingest it. So of course the point is that you have to become more engaged in your learning that way. It's less digested. And I mean, you all passed the bachelor's physics program. So unless we did you a great disservice, hopefully you've seen some of this stuff already. So we could go a little faster, and we could also go at a slightly more advanced level. Does mean that we'll do less. We'll do less really digging into the problem space, because it's just not good use of time. With the exception of sometimes when we do new things. So today we're going to do Maxwell energy stress tensor, which really only takes up a couple of pages in the book. But I think it is very, very valuable for us to really go through what it means and how to read it and how to construct it and how to do problems with it, because it's the first actual tensor that you see. And then you'll actually also be able to see it at work, because it's a tensor, it's very hard to visualize what's happening, because it's not a vector field, it's a tensor field. So you can't do diagrams anymore unless you do projections all the time. So we'll work with that, and then we'll do that. Okay. So today we are continuing our work with the electromagnetic energy, but we will look at a slightly different aspect of it. So we had the Poynting vector that we called S, and oops, that is running out of space. We called it S, and that was 1 over 4 pi c E crossed with B. So this is the it's the energy flux. Okay, so we need to talk about what we mean by energy flux. What that means is that if you have some kind of a flux, let me draw it. So let's say we've got some flux that is going in this direction. This is all, this is all this Poynting vector S, and it's pointing in a certain direction S. That means that the energy is traveling in that direction, and that means that if you place a surface here, so some surface here A, that all of that energy is going to get dumped into that surface, which is, for instance, what how solar panels work, right? So all of that electromagnetic energy, which is carried by photons, gets converted to electrical energy. So you're basically kicking your electrons or your holes in the semiconductor to a different energy level, and then you convert that incoming energy that's carried by this thing that's described by the pointing vector into electrical energy, and then you can charge your cell phone. So so that's what we mean by the energy flux, and it's the it's the flow of energy, right? Now there's an associated vector property that's called the momentum density. And that momentum density we're going to call G, lowercase g, and it is equal to that pointing vector over c squared. And what do we mean by momentum density? Well, we have this flow of energy, and per unit time, this energy, because it's carried by waves with the speed of light, this energy, which is let's say contained here, could get deposited onto a surface there and then transfer momentum to that thing. So what we mean by that is basically the momentum gets, sorry, I'm mixing my words. So the momentum could get transferred, which means that this object here could get some momentum at the expense of the loss of momentum in the electromagnetic wave. Or thinking about it differently, if you're standing there, you would feel pressure if you are absorbing that momentum. So, so the pressure that is associated with that, pressure is actually the derivative of that momentum density. And now we are hopefully in familiar water, because that is just, let's say, in the SI unit system, it's pascals, right, or pressure in pascals. It's directional, so it's going in a certain direction. But for instance, in the SI unit system, this means that in SI, this is pressure, so a bar or atmospheres or newtons per square meter. And of course, we're not doing this in newtons right now, but this should be familiar territory. So we went from pointing vector to momentum density, which is useful, and then we ended up in pressure. So let's look at what that pressure looks like, because we can go back, right? So there, our G is defined as the pointing vector over c squared, and now we need to take the time derivative. So now we have stuff that we can do calculations with. Okay, so let's see what we get if we take the derivative. I think I might be missing factors of c squared here for a second, but okay, let's not worry about that for now. Okay, so the this dg dt is going to be the ddt of our pointing vector 4 pi c, and then that is our E crossed with B. Okay, so our job for today is analyze this expression. So let's do a couple of things. So first of all, let's pull out our 1/4 pi c, and then second of all, let's actually start write cross products cross products with the Levi-Civita symbol. So for instance, so remember that if you have some cross product A with B becomes C, then in tensor notation, it is epsilon I j k A j b k. Okay, so using that notation, we can write our derivative. So that's ddt, and that is epsilon I j k E j b k. So I haven't really done anything yet. I just wrote it in tensor notation, but now we are talking about the ith component of that pressure. So the only hanging index right now is the I here. So let me make sure that I highlight that. So because that's the only hanging index, actually, this is right now the ith component of that same vector. So we went from a vector notation to a component notation, and the j sum and the k sum are implied because we have the that index repeated twice. All right, and now we're going to do our we're going to start differentiating this. So the epsilon does not differentiate, so ijk. And now we will get a sum of two terms because we have the product rule. We'll first get the derivative of E. So that is d dt of E j times bk, and I'm putting my bk in front. So just to make it super clear that that's actually the one that is not being differentiated. And then, of course, we get our EJ and then ddt of BK. Okay, so we haven't done anything yet. We've just used the product rule. Now, this is where we invoke Maxwell's equations, because we can do something with this and we can do something with this, because they show up in Maxwell's equation. So we're gonna first look at the blue term. So the blue term says that it's the time derivative of the magnetic field, right? So that one shows up in Faraday's law. So in Faraday's law, we have that the curl of E is minus dB dt. So, but now let's write this in vector notation. So it's actually the curl of E. So that is, oops, it's epsilon I j k curl. Now that's the derivative. So now we need a d dx j, and then we need an e k is then equal to the derivative of the b, but that's the ith component. So that's the thing that we will need. Now we have to be really careful, because we already had an epsilon ijk, and we had an implied summation. So we cannot just dump this expression in, because now we're going to get index confusion. So we have to rename our indices using new indices that we have not used before. Ultimately, what we will end up, or have to end up with, is as a hanging index that is free, is the one that is actually currently in use in this expression by the magnetic field that we take the time derivative of. So in other words, that I needs to be a K if we want to be good. So let's start changing this a little bit. So the I's become K's. Okay, and then oops, and then the oops, i's become k's, and then we have to relabel our j's and our k's because we cannot use them twice. Okay, so nope. Sorry, I'm having color issues. That's BK. So that's the hanging index. That's the one that's not being summed over, and that is in the Levi-Civita symbol is the first one. And then we have a K, we have an L, and an M, for instance. And then L is the first one, and the M is the second one. So now we have renamed it, and now we are free to insert this thing into the equation. But we also have to deal with the green expression. So let's look at the green expression. So the green expression is the time derivative of the electric field, which shows up, of course, in Ampere Maxwell. So in Ampere Maxwell, we have the curl of B is 4 pi over C J. And now I know I'm using J as the current density vector, and I'm also using it as an index, but that cannot be helped because life's too short. And then this is our displacement current, and that's of course where we need our dE dt. All right, so we have our dE dt there. So that means that we need to rewrite this expression in terms of that time derivative. So we'll bring over our dE dt over to the other side. So we have 1 over C dE dt. And then I'm going to throw away the C. I'm going to bring it over to the other side. So we have a C curl of B minus 4 pi J. And now we're going to rewrite this in tensor notation. Then that means this is going to be ddt of E, and that is going to be C times an epsilon, and we need also a dx here, and we need a B, and we need a minus 4 pi J. Now we need to decide what hanging index to use. So we have, in this case, we need an EJ. So that means that we want this J here. So that's our hanging index. That's the first index in the Levi-Civita. And it's also, therefore, the thing that we need the current density for. So that's going to correspond to the J component of the current density, which unfortunately, again, also is J. And now we have, we need 2 more symbols. So let's not use L and M, but let's use N and O. So then this becomes an N and this becomes an O. And then we are done. And then we can actually insert that into our equation. So hold on to your hats because it's going to get a little big. Okay, so we have 1 over 4 pi C, and we have an epsilon I j k, and then we have a bk times the ddt of ej, which I'm not now going to put in. That's the green expression. So that is now C times epsilon j n o, and now this is the ddxn, which I'm going to write as dn, and then bo minus 4 pi j vector jth component. All right, so that's our first term. So that's the incorporation of the green term. And now we need to incorporate the blue term. So we will do the same thing. So 1 over 4 pi C. And the blue term is going to look ijk. That's an EJ. And now the blue term. And the blue term is not as big. it's our epsilon K L M. And now I am going to write this dl and E M. And then we are done. So all we've done so far is we have figured out how to write those time dependencies that we had, because we took the ddt, so the time derivative of the Poynting vector, because that's going to tell us what the pressure is, and we wanted to get rid of those time derivatives, and then we were able to use Maxwell's equations to write those in terms of spatial derivatives. So now we went from the time derivatives to spatial derivatives, and this is why we have, all of a sudden, we have these here. Okay, so I had dropped an extra C in here, and I had this minus sign missing as well. And therefore, we have an extra minus here and an extra C here, and those showed up here. All right, now comes the really tricky part. There is an identity for the double epsilon product, and this is where we are going to use nearpod. So simplify using, and I'll tell you which equation it is, 530 from the book. Sorry, 533 from the book. First, the green one, so it's an epsilon I j k epsilon j n o, and then the blue one, so that's epsilon I j k epsilon k l m. All right, so this is the reference equation. The way to look at this is, so we're summing over I, right? So the I here is the thing that you're summing over. So those should not appear in those delta functions on the right, because they are already summed over. The first two delta functions have index JL and KM, which are J, L, and KM. So those are index 2, 2, and 3, 3 on those Levi-Civita symbols. And the second delta has JM, which is therefore it's the J combined with the M, so it's the second with the third, and the K and the L, so K and the L. That's the third and the second. So that's the way to read it. Now, the only thing we need to do to our green and blue double Levi-Civita product is we need to shuffle the I and J, because the way it's written right now is we're actually summing over the J, and the J in this first epsilon is in the wrong location, if you want to think about it that way, to apply that red transform rule. So we're going to use the fact that if you swap any of the two integers in the epsilon, you just pick up a minus sign. So that becomes a J, I, K, and now there's an epsilon, J, and O. Okay. Okay, now here we go. That is minus. Okay, we're going to do a delta. Now it's the second with the second and a third with the third, right? So that's an I and an N. And then the third and the third are the K and the O. And now the delta second and third, so that's I and O. And the third and the second, so that's a K and an N. Okay, so the IJK needs to be shuffled a little bit differently, because the K is the thing that we're summing over, and the K shows up as the third index on the first epsilon. So we're shuffling those with the I, and then we get now minus, and now our delta system. So we get J, L, delta, I, M, minus delta, J, M, delta, IL. Close parentheses. And now use that. So we have an EJ and a del LEM. And we need to multiply that with delta JM, delta IL, minus delta JL, delta IM. All right, so our first two indices will mean that the J becomes an M, so that becomes EM, and then del I EM minus, okay, and then we do a JL, so the J becomes an L, so that becomes EL. Then the L we already had, and the M we keep. So and we might as well make this one, keep that as an L. So we have more symmetric terms. Okay, so that's the first one. And now onto the green one, we have a BK and a del N and an EO. Okay, BK del N, sorry, BO. All right. And that times that second delta system, so that's a delta IO delta KN minus delta IN delta KO. So that also becomes two terms. So the O becomes an I and the K becomes an N. So we get B N del N B I. Now minus let's see if I'm doing this right. Yes. K becomes an O, so that becomes B O del N B O. There we go. So those are our two terms. We have them correct now. Let's change it a little bit. So we are here. We end up getting something that is the ith component of something, right? So we need to make sure that that I survives and that we don't swap it out for a dummy index. So the ith component here became the del L in the first expression. So I'm going to change that to a del I. And the M, sorry, oh, I'm doing it in the wrong way. This one becomes I. And the M was a J, so let's go back and let's call those J's. Doesn't really matter here because we're actually summing over it, but it's always good to, those two we're summing over, but it's always good to go back to them. And then the second term, we had a J for an L, so we put an L in, but let's put a J there. So that's J. And then the I and the M, of course, we want the I to survive. So that is I. Okay, now same thing with our second expression. So we had a BKDNBO, and that first was an I for an O, that's fine. K for an n. Let's call that one a K. And an O for a K and an I for an N, so that del N becomes del I, and O's become K's. K, K, I. All right. Now we have it as we have it in a slightly easier digestible form. So we have an I and an I and a K and a K. Yes. Yes, yes, we do. Okay. So putting the whole thing together, the green and the blue, we are back at our original expression that we had our G, T, the I's component, and we have 1/4 pi, and this is our first expression is EJ, and there's a minus here somewhere too. Yeah, dropped a minus. So we get EJ, DJ, EI minus EJ, DI, EJ plus. Now we basically get the same thing, but now for the B component, BI minus BJ, I, BJ. That's our first term. And then we have minus 1/C, and then we still have that cross product of G cross B, J plus B, because we didn't actually change that when we had our original expression here, G, we crossed that with the B here, and we didn't actually change that with our epsilon manipulation. So we still need to keep that cross product. So that's why it's still there. Okay, now this first one, we're going to write as del J E J E I minus E I del J E J. So it's the inverse of the product rule, right? So the first term, if you take the derivative, you get two terms. You get a del J EJ times an EI, and you get a EJ times a del J EI, and we only have one of those, so we can take care of the other one. Now, the del J EJ is actually, you might have not recognized this, but this actually says the divergence of E. So that is 4 pi rho. All right, and then this term we can write as minus 1/2 del I, and then we get an EJ EJ, right? Because we do that twice, and that is the inner product of E with itself, which is E squared. So we do that, and we do that for both. Then we get the EI times 4 pi rho. Those two get added over here to the right. So then we have a rho and a J and a B and an E in the usual combination. And now we have for the other part, we have so we have del J E J E I minus 1/2 del I E squared plus del J B J B I minus 1/2 del I B squared plus there's supposed to be a EI rho plus a 1 over C J crossed with B and the ith component. I think I'm having a couple of signs wrong here. Yeah, I think I have a couple of signs that are wrong. Yeah, there's a minus and a plus. Yes. Okay. Now, after all this heroic effort, we have, I hope that you see this, this d of j is the derivative with respect to the jth component. So it's like the gradient, if you want to think about it that way, but we're also doing a sum over j. And then only when j is equal to I do we subtract this del I e squared. So that looks like Kronecker delta. So therefore, we can write it as the derivative of the following. So it's the derivative of del j of, and I'm gathering my e squared, oops, and b squared terms. And those go here. And then there's a minus. Plus the remainder, EI, EJ, and plus BI, oops, BJ. Yes, and then minus the rho EI term plus the 1 over C J crossed with B, the ith component. Okay, now this, ladies and gentlemen, is together with the 4 pi is the Maxwell stress tensor. And it shows up in the following manner. So we have our pressure, right? So that's our d, g, dt. The ith component is minus del j t I j. Okay, minus rho EI and minus 1 over C J crossed with B I. So this is the stress tensor. Now there are two tricky parts about reading this. The first is that this term is actually the change in the mechanical momentum, and the green term here, that is the divergence of the stress tensor. Why do we call it the divergence? So remember when we have, for instance, so compare we have a divergence of E. We can write that as del J E J. It's the same thing. So we're doing the same thing now. So we're taking the del J and then summing over the Jth component of that stress Maxwell stress tensor, but it's not a. Afterwards, there's still an ith component left, and that's why it's a tensor. So when we take the divergence of the electric field, we go from a scalar field that is a tensor field of rank 1. So basically meaning it has only a single index. We make it into scalar. So by taking the divergence, you compress, you contract over one of the indices and then are left with a scalar. Now we have, if you want to think about it, a two-dimensional two-dimensional grid that we need because we have two indices. We take the divergence, it becomes a vector. So that's why the dg dt I is a vector, and the divergence of that tensor gives you that vector. All right. Now, if we now want to see what that tensor looks like, we can organize it. You see, it's got so it looks like this: T, I, J. It's got on the diagonal has these 1/2 e squared plus b squared terms subtracted. So e squared plus b squared terms all across the diagonal. And then added to that is the case here where I and j are the same. So that means that this becomes positive. So this is positive e squared plus b squared. And the off diagonal elements will be, for instance, ex ez plus bx bz. And that's what this tensor looks like. Okay, now what does the tensor actually do? What does the Maxwell stress, oh, come on, tensor do? Well, if we have a we have the momentum density, right? So we can integrate that, and then it becomes a volume density. So if we do a volume integral over the that dg dt I, so we're integrating that over the volume, we can now do that with the del j t I j integrated over volume, and then plus the mechanical density dot integrated over the volume. And the first term you can change into a surface integral, and then it becomes the T Tij with the normal of that surface out. So this is the surface, and that is the normal pointing in the I direction. Okay, so this is actually the pressure on the ith normal due to E and B fields. So let's put that to use. So let's say we have a magnetic field that is in the z direction. So this is our B, and it's just B times B in the z direction times z hat, and all the other components are 0. So that's an example, and it's static, and E is 0 as well. And now we can ask ourselves, what is that stress tensor? Well, if we go back to the stress tensor, of course it was on the previous page, you would find that the x and the y components are both that z over 8 pi, because there's that 1/2, and the z component is minus b sub z squared over 8 pi. Okay, so how do we read this? Well, if this is the pressure on the ith normal due to that tensor, then the pressure, oops, the pressure in the x direction is the pressure in the x direction is the so it's the minus, that's the x, and then the normal in the x direction integrated over that surface. So if we're putting a surface here, let's say we call it a Gaussian surface, and we have our coordinate system, so x, y, z, x, y, z, then this pressure and this pressure are evaluated by taking the x component of the stress tensor and then multiplying that by the normal. Now, hopefully you see that if the normal is pointing in the opposite direction, but the stress tensor has not actually changed, there should not be a net pressure on this should not be a net pressure on this cube. The only way you can get a net pressure on a cube is when you move it out of the magnetic field. So for instance, if you move it out, so the black cube, for instance, we're moving it out to, let's say, the edge here. Now we get a net pressure, and then the pressure is in the x direction. Pressure in the x direction now is b squared over 8 pi, because the stress tensor on the right is 0, right? So here txx is 0 because b is 0. So therefore now there is pressure there. So the way to think about this stress tensor is that it is very sensitive to changes in the magnetic field, right? Because we had no pressure when this Gaussian surface was inside of the magnetic field, because those two terms on those faces, they cancel. But once we cross that boundary, now we have a net pressure, and this pressure is real. This is actually the thing that if you take a solenoid and you make a solenoid. So let's say we call it. So we have a solenoid, and we have a magnetic field here, and even if it's static, then basically at the edge here there will be pressure on the windings of that coil, and therefore if you don't hold those wires together, the whole thing will basically try to unravel itself. So this inductor or solenoid would unravel itself. Due to the txx gradient at the edge. And so that's for static magnetic fields. Now another example we could do is we could do static electric fields. And that is actually a problem from in the book. So if you have an ideal parallel plate capacitor, you could have, you have your E field. It's some E times Z naught. And then we can ask ourselves the question, okay, where would we find the gradient? So in this case, we're not looking at a gradient in the magnetic field, but we're looking for a gradient in the electric field. And obviously that is going to happen when we cross either one of these planes. So if we put our Gaussian surface here, and it basically pokes a hole in this plane, then we will have T is 0 over here and non-zero there. So therefore there will be a pressure on these two plates. And that's definitely going to be one of the homework problems.